In today's video lecture, we are going to talk about one-dimensional conduction for radial systems, so for cylindrical and spherical systems. In the previous lectures, we've talked about one-dimensional conduction for plane wall systems. In radial systems, it gets a little bit more complicated, but it's still not too bad. So our first example, we want to develop a tube wall temperature profile. So if you can imagine a tube or a pipe with an inner radius of R1 and with an outer radius of R2 with known temperatures. So the surface temperature at the inner wall is TS1 and the surface temperature at the outer wall is TS2. Our objective here is to figure out how does T vary with radius, where radius is going to be greater than R1 and less than R2. So somewhere within that tube wall, we want to define the temperature at any given R. So we start with the heat equation in cylindrical coordinates. A tube is a cylinder, so this is a natural coordinate system to use. We are going to make some assumptions here. So the solution we'll develop will be for steady state conditions, which means we're not going to be concerned with how the temperature changes with time. We're going to assume that the surface temperatures are held constant until the system reaches a steady state. We're going to assume that temperature is not a function of z. So if this were a big long pipe, and this is the z dimension, so the distance axially down the pipe, we're not going to be concerned about temperature variations in that direction. So we'll assume that dt dz is 0. And we're also going to assume that temperature is not a function of an angular coordinate phi. So in this direction, phi, we're not concerned with temperature variation, so we can assume that dt d phi is 0, and we can neglect this term. And we're also going to assume that there's no generation happening. There's no source of heat inside the pipe itself. So no generation, so that term is 0. So that leaves us with a much simplified version of the heat equation. We're only considering variations in one dimension, no generation, and we're at steady state, so we don't need to worry about the accumulation term in this particular case. So that leaves us with 1 over r times the partial derivative with respect to r of the thermal conductivity times r dt dr, and that quantity is now equal to 0 because there's no accumulation. And if we make one more assumption that the thermal conductivity is constant, doesn't vary with temperature and doesn't vary with space, then we can actually pull this out. So we can get rid of that and bring it out of the derivative, that outer derivative. So one trick we can do here is, so if you'll recognize that we have a product of two different terms, we have k over r, and we have this these derivative terms. Let's go ahead and get rid of the k in there because we've moved it out. Alright, so we have a product of two different terms that's equal to 0. Well, we're dealing with r, we're dealing with a finite r, because we know that r isn't 0, r is going to be somewhere between r1 and r2, as we've defined previously. And we're going to assume that k is non-zero as well, which is true for basically any material. So we know that this term is finite. It's non-zero. Which means when you multiply a finite number by something and that product equals 0, well, the other term that you multiply it by must be 0. So that lets us get rid of this term. So now, and one step I forgot to include is we're no longer dealing with a partial differential equation. This is an ordinary differential equation. So our equation now becomes d by dr multiplied by this quantity r dt dr is equal to 0. So now we have a much simpler equation than we started out with, and we can do some separation and integration to develop this temperature profile. So one of the first steps we will do is we'll take our equation d by dr, r dt dr is equal to 0, and we're going to separate and integrate. So that leads us to the derivative of r dt dr is equal to 0 times dr. And if we were to integrate each side, we get r times dt dr is equal to the integral of 0 dr, which is not 0, it's a constant. So we have a constant of integration there. So now if we do some rearranging, we get dt dr is equal to C1 over R, and the next step is multiplying both sides by dr, so we get dt is now equal to C1 times dr over R, and if we integrate this side now, that leads us to this solution. So we have the temperature is equal to C1, and the integral of dr over R is the natural log of R. And now we have another constant of integration. So we have plus C2 there. So here we have this generic form of the equation. But we want to make this more specific. We don't know what C1 and C2 are at this point. So then we want to apply our boundary conditions. So when we apply our boundary conditions, those boundary conditions are at R equals R1, we have a surface temperature of TS1, and at R equals R2, we have a surface temperature of TS2. And very similarly, at R equals R2, we have T is equal to TS2. So knowing these two temperatures will help us to put more definitive terms into our temperature profile equation. So when we substitute in our boundary conditions, we get TS1 is equal to C1 times the natural log of R1 plus C2, and we also get another equation, TS2 is equal to C1 times the natural log of R2 plus C2. So all we did was we took these conditions, R1 and TS1, and substituted them into this generic equation to get a more specific equation for which we can use to solve for C1 and C2. So both of these equations look very similar, and one thing we can do is we can solve for C2 in both equations and get an equality that's going to help us out. So C2 is equal to TS1 minus C1 times the natural log of R1. And if we solve this equation, we can get another, if we solve this equation for C2, we can get another equation, which will be useful. So we get TS2 minus C1 times the natural log of R2. That is also equal to C2, which is also equal to this equation. So we have this nice equation that should come in handy later. So we'll come back to C2. And what we're going to do is we're going to solve this equation for C1. And when we do that, we end up getting so I'm going to take this equation, I'll just walk through the algebra a little bit more. I'm going to take this equation, I'm going to move TS2 over to this side by subtracting, and I'm going to move this term over to this side by adding. So that gives us TS1 minus TS2 is equal to C1 times natural log of R1 minus natural log of R2, which is also equal to C1 times the natural log of R1 over R2, just by applying that identity for the natural log. So, solving for C1, we get C1 is equal to surface temperature 1 minus surface temperature 2 divided by the natural log of R1 over R2. And we'll just keep that handy somewhere. And I'm going to go back and get our definition for C2. So I'm going to substitute, I'm just moving this onto the other slide so we can see it later. So now we have C2 is equal to TS2 minus C1 natural log of R2. So just taking that equation and putting on this next slide. All right, so now if we go back to our generic equation, we had the temperature as a function of R is equal to C1 times natural log of R plus C2, and now we just substitute in these equations. So that is equal to C1 times the natural log of R plus, and I'm going to substitute in C2 here, so plus TS2 minus C1 times natural log of R2. So if we do some rearranging, that happens to be equal to C1 times the natural log of R over R2. So we've taken this term and subtracted, we've taken this term and subtracted this term, and then we've applied that same identity where the natural log of R minus the natural log of R2 is equal to the natural log of R divided by R2 plus TS2. That's the last part of our constant C2. So now if we substitute in C1, we will have this complete equation defined, giving us the temperature as a function of R, and it's defined entirely of terms that we should already know. So if I make the substitution for C1, I get TS1 minus TS2 divided by the natural log of R1 over R2, and then that quantity is all multiplied by the natural log of R, and then we still have to add in our other surface temperature. So if we know those surface temperatures, TS2 and TS1, and we know the radii, we can come up with an equation that gives us the temperature profile as a function of the things that we know. So if we wanted to figure out what's the temperature somewhere here at R1 plus some delta R, so we can just take whatever R1 plus delta R is, let's call it 5 millimeters, and we would just plug in 5 millimeters into here, and that would give us the temperature at R equals 5 millimeters. So we've gone through the derivation already, and this is what our textbook gives us for the temperature profile of a tube wall. So again, we're looking at R1, R2. This was the form of the heat equation that we solved, and I just walked you through how this temperature distribution is derived, starting with the heat equation. Alright, so now let's do a thought question. So, true or false, in a cylindrical system at steady state, the heat flux is constant with respect to R, because we just apply Fourier's law that flux is equal to minus K times dt dr. So stop and think about that. Is flux going to be constant? So I'm going to draw a cylinder at various distances out. And let's say we have some generation term in here. So is flux going to be constant? So this is actually false. This equation is correct. Fourier's law applies for sure, but the temperature actually changes with respect to R in a nonlinear fashion. So you can see that we have natural log of R showing up. So that means dt dr, the derivative of this equation, is not going to be constant. So we will not have constant flux at any point. And remember, flux is defined in watts per meter squared. So because we are not going to have a constant derivative of our temperature profile with respect to R, we will also not have constant flux. This is different for the plane wall system. Remember, a plane wall system with no generation, and at steady state with a constant thermal conductivity, we expect for our temperature profile to look something like this. It has a constant slope. That's different in a radial system. Another way to think about this is that if we have uniform heat generated inside of our cylinder, inside of our tube wall, that heat is going to be encountering a larger and larger cross-sectional area as it as it conducts outward. So each of these circles gets bigger and bigger in terms of surface area, so that heat is dissipated as it goes out, so our flux gets lower and lower. So that answer is false. So here are some different terms. These are equations that apply to this scenario. So steady state, constant thermal conductivity with known surface temperatures on the inside and the outside of the tube wall. Our flux is defined like this, and we won't derive the flux in this case, but one way you could get the flux, so flux is defined as minus k times dt dr, and we just derived what Tr is, temperature as a function of radius. So you could go back and differentiate that temperature profile, multiply it by minus k, and you would come up with this flux term. And this indeed verifies that flux is not constant with respect to R. The flux as R gets bigger, the flux gets smaller and smaller because we have this 1 divided by R. If we are to multiply by the perimeter of the cylinder at any given R, we can get the heat flow per unit length, which is just in watts per meter. And again, that heat flow per unit length of the cylinder, it has this R term in there, so it depends on which R you're trying to quantify it for. And if we wanted to get the absolute heat rate coming out, this term is actually expressed independent of R, but you notice that we have to put in R1 and R2 into that term. So to get the total amount of heat generated as you go outward radially, we can apply this equation. So using this equation, we can now solve for what the conduction resistance is. So the conduction resistance for a cylindrical system is defined here. And again, this term is independent of R, because now we're no longer talking about the flux, now we're talking about the absolute amount of heat that makes it from inside to outside. And if we know R1 and R2, we can determine what that absolute rate of heat coming out is, which lets us to easily define a thermal resistance. And that thermal resistance can also be applied for unit length with this equation. But you'll notice that there's the conduction resistance here isn't given for surface area, because we know that the flux actually changes the farther and further out you go radially. It can be useful to define an overall heat transfer coefficient times area product, just like we did for the plane wall system. So that is just the inverse of the total thermal resistance. So here you see multiple tube walls in series. So we have heat trying to propagate from inside, and it has to conduct through multiple different materials. We can again use this thermal resistance method, but those thermal resistances are now have these natural log terms in there, but they're still going to be in series in this case, so those would just be additive. And we can define a term, so we'd get the R total by just summing up all the different resistances. And you notice that the convective resistances include the perimeter and the length. So we can get the total thermal resistances just by adding them up. And we could find this U times A product by taking the inverse of the total resistances. One thing to keep in mind is that U itself is not constant because that heat is encountering different cross-sectional areas as you go out radially. So that same basic idea we've been discussing. But the product U times A, that can be considered constant. But because A is changing, U would also be changing. So think of U and A in this case as a single variable and not as two different variables because it's not particularly useful to think of them separately. You want to think of them together in a cylindrical system like this. So we're now going to move on to a spherical shell. So we're going to be looking at spherical coordinates, and we're going to get a temperature profile going out radially if you have a sphere. So the derivation would be very similar. We'd start with the heat equation, and we'd solve the heat equation under steady-state conditions with no variations in the two different angles in spherical coordinates, just radially. So we start with this version of the heat equation, and we would just integrate the heat equation with our boundary conditions. So here would be TS1, and here would be TS2. Since we've already gone through a long, drawn-out derivation for cylindrical coordinates, I'm going to spare you the derivation for spherical coordinates. But that temperature distribution looks like this, but it's the same basic method. You integrate the heat equation, and then you apply your boundary conditions. Use those to solve for your two constants of integration, and your temperature profile ends up looking something like this. Okay, so let's do an interactive question. In a spherical system with heat generation uniformly coming from its center, how will the heat flux vary with R at steady state? So let's assume you have a hollow sphere. So now this is a sphere. And we have generation going out. So this is going out. This heat eventually is going out in every direction uniformly. So there's no variation with respect to the different angles, phi and theta, that we use for spherical coordinates. So how does heat flux vary with radius? Is it going to increase with radius? Is it going to decrease with radius? Or is it going to stay constant with radius? And I'll give you just a second to think about it. So the heat flux is going to decrease with radius, and it's the same concept as we talked about in cylindrical coordinates. We have a constant rate of heat going out in all directions spherically, and as it encounters, the more it propagates outward, the smaller that flux is going to get. So we have a constant amount of heat going out, but it's encountering larger and larger cross-sectional areas as R gets bigger. So this is the same, if you think about the sun propagating out heat in all directions, the further you are away from the sun, the less amount of heat per unit area you're going to get. So it's the same concept here. Okay, another interactive question. In a spherical system with heat generation uniformly coming from its center, how will the total heat rate Q vary with R at steady state? So now we're not talking about flux anymore. We're talking about the absolute amount of heat in watts. How is that going to vary with R? Is it going to increase with R, decrease with R, or remain constant? So in this case, we're talking about the absolute amount of heat. So this would be flux times surface area. So while flux will be decreasing, surface area will be increasing with r, because the surface area for a sphere is equal to 4 pi r squared. Flux, coincidentally, will be decreasing by proportional to 1 over r squared, so those terms cancel out, and we get that the total rate of heat in watts coming out spherically stays constant. So again, if we were to take our temperature profile and differentiate it and then apply Fourier's law, we could derive what the heat flux is. And you can see heat flux does vary proportional to 1 over r squared. So that flux gets dimmer and dimmer. It gets less and less intense as you go out radially. However, the absolute rate of heat doesn't have the r squared term in there. It's constant. That heat is coming from the center and it's going to be propagating out in all directions, and even though the flux gets diminished, this is made up for by the surface area getting bigger and bigger. So using that equation, you can define a conductive thermal resistance for a spherical system, and specifically the spherical shell. So the same concept applies, where this UA term, the overall heat transfer coefficient times area, is equal to 1 over the total thermal resistance. So that term is constant. The product of UA is constant, but because the surface area gets bigger and bigger the further out you go, U does not stay constant. It actually gets smaller and smaller. So it's useful to think about this constant product, and not quite as useful to think about U by itself.